You hit shuffle on your favorite playlist. 3 songs in, the same artist plays twice in a row. By track 7, you've heard 2 songs from the same album and your favorite band hasn't shown up at all. So you do what everyone does. You mutter that shuffle is broken, that Spotify is pushing certain tracks, that the algorithm has an agenda. But here's the strange part. The original shuffle, the one engineers built first, was mathematically perfect. True, pure, uniform randomness, and users hated it. They complained so loudly that Spotify had to rip it out and replace it with something deliberately less random. So the question is this: why does true randomness feel rigged to human ears? And what clever trick did Spotify use to fake fairness better than fairness itself? Let's start with what random actually means to a computer. When Spotify first launched Shuffle in 2012, they used what's called the Fisher-Yates algorithm. Picture a deck of cards. You pick a card at random from the deck and put it on top of a new pile, then pick another, put it on top. Keep going until the old deck is empty. The result is a perfectly shuffled deck where every possible ordering is equally likely. Mathematicians love this. It's elegant, it's provably uniform, it runs in linear time. Spotify shipped it, and then the support tickets started rolling in. The complaints all sounded the same. Shuffle keeps playing the same artist. I heard 3 Beatles songs in 10 minutes. It's clearly favoring certain tracks. Engineers checked the code. The code was fine. They ran simulations. The distribution was uniform. Statistically, mathematically, provably, Shuffle was working. But users weren't wrong either. They really were hearing clusters. Because here's the uncomfortable truth about randomness. Real randomness is clumpy. If you flip a fair coin 20 times, you'll almost certainly see a run of 4 or 5 heads in a row. That's not the coin breaking. That's what fair actually looks like. You can see this with a simple visual test. Imagine throwing 100 grains of rice on a table. If you scatter them truly randomly, you'll get clumps. Dense patches here, empty patches there. If instead you carefully spread them so each grain is roughly the same distance from its neighbors, the result looks orderly, intentional, almost designed. Now here's the kicker. When researchers show both patterns to people and ask which one is random, almost everyone picks the spread out one. The truly random pattern looks rigged. Our brains evolved to detect patterns, and we treat clusters as evidence of cause. A run of 3 Drake songs feels like an algorithm pushing Drake, not like the dice doing what dice do. So Spotify faced a design choice. They could explain statistics to 200 million users. Good luck. Or they could redesign Shuffle to match what humans expect. They chose the second. The new Shuffle is built on a simple insight. People don't want random. They want variety. They want their listening session to feel like a thoughtful DJ picked the order, spreading artists out, mixing genres, never repeating too soon. Which sounds easy until you realize you have to do it for a playlist of 50 songs across 12 artists in milliseconds for 500 million playlists without anyone noticing the trick. The first attempt was easy to describe: group songs by artist. For each artist group, spread their tracks evenly across the playlist timeline. So if you have 10 Beatles songs in a 100-track playlist, you space them roughly 10 positions apart. Then jitter each position a little so it doesn't feel mechanical. Do the same for every artist. Merge. Done. This is sometimes called stratified shuffling, and it works, but naively it's slow and clunky. You have to recompute positions every time, handle collisions when 2 artists land on the same slot, and rebalance constantly. For a single playlist, fine. For Spotify's scale, you need a data structure that does this fast. Enter the heap. Specifically, a priority queue. If you've never met one, here's the idea. A heap is a tree where every parent holds a smaller value than its children, or larger, depending on flavor. The magic is that finding the smallest item is instant, and inserting new items or removing the smallest one takes time proportional to the log of the size. For 1 million items, that's about 20 operations. Fast, predictable. Exactly what you need when 500 million users hit shuffle at the same time. Here's how Spotify-style shuffle uses it. Every song gets assigned a target position, a number between 0 and 1 representing where it ideally sits in the playlist. Songs by the same artist get target positions evenly spaced, with a small random offset so it feels organic. Then every song goes into a priority queue, sorted by target position. You pull songs out one by one, smallest target first, and that's your shuffled order. The result, no artist clusters, no obvious pattern. Every shuffle feels different, but the variety is engineered, not gambled. Let's see why the heap matters here, not just any sort. Imagine a playlist of 10,000 tracks. You could compute all targets and sort once. That's n log n work. But Spotify's real system has to handle changes. You add a song, remove one, like a track which boosts its weight, skip one which lowers it. A heap lets you insert or remove a single item in log n time without resorting everything. It's a living, breathing structure that stays organized as your taste shifts. That's the deeper win. Not just speed at startup, but speed at every interaction. But there's a twist. Pure spacing alone makes shuffle feel too perfect, too predictable. If you always heard Beatles, Stones, Drake, Beatles, Stones, Drake, you'd notice the rotation just as fast as you notice the clusters. So Spotify adds controlled randomness back in. Each target position gets nudged by a small random amount. Each artist's phase, where their first song lands, is randomized. The result lives in a sweet spot, random enough to feel surprising, structured enough to feel fair. It's not uniformly random and it's not deterministic. It's something better, something that matches the shape of a good DJ set. There's an extra layer worth mentioning. Spotify also weights songs by listening history. If you've skipped a track 20 times, its target position gets shifted later in the queue, or its probability of appearing at all drops. If you've replayed a track on loop, it can surface earlier. This is where the priority queue really earns its keep, because adjusting one song's weight just means updating one node in the heap and letting it bubble to its new spot. No resorting, no rebuilding, no lag. Your shuffle is personalized in real time, and the structure makes that possible. Step back and look at what happened here. A team of engineers spent real effort making their product less mathematically correct on purpose. They violated the textbook definition of randomness to better serve human perception. And it worked. Complaints dropped. Users stopped accusing the algorithm of bias, and the system became the industry standard. Apple Music does something similar. So does YouTube Music. So does almost every modern shuffle you've ever used. The random in your pocket is a careful illusion, engineered by data structures most users have never heard of. And this points to something bigger about software design. We tend to think of correctness as a single thing. Code either does what it's supposed to or it doesn't. But Spotify's shuffle shows there are two kinds of correct. There's technically correct, which satisfies the math, and there's experientially correct, which satisfies the human. When those two diverge, good engineers chase the human. The lesson isn't that randomness is bad, it's that the goal of a product isn't to model reality, it's to model expectation. The heap is just the tool that made it cheap enough to do at scale. So next time you hit shuffle and your favorite song comes on third, or your least favorite artist mysteriously stays quiet, know this. It's not random. It's something more thoughtful than random. A priority queue is quietly arranging your evening, spacing artists like a careful host, seating guests at a dinner party, making sure nobody dominates the conversation. The math behind it is over 50 years old. The data structure is taught in week 3 of any computer science course, but the insight, that fairness sometimes means breaking the rules of fairness, that's the part worth remembering. Because the best engineering doesn't just solve the problem, it solves the problem you actually had.